Hello, professors. My name is WeiZhu, and firstly, I'm very sorry about my computer camera is here, and it looks like I'm talking to you using my nose. I'm very sorry about that. Today, I would like to introduce my project to you. This presentation is divided into four parts. The first part is an introduction about the background and motivation. With the rapid development of the Internet of Things, the IoT is already relevant to us in traditional areas, such as building automation. For example, in our daily life, we can use IoT technology to control our home appliances via our smartphones. Meanwhile, the IoT is also used in medical applications. For instance, the doctors operate on patients in the operating theater with the aim of the smart devices and monitoring equipment. The increasing popularity of the IoT has led to a huge number of operational data, which is often unstructured and various. This vast and complex data is referred to big data. The data is constantly produced and transmitted from edge applications and IoT devices to cloud applications. After data has been processed and analyzed in the cloud, it is stored in the cloud and or turned it into other forms of data and returned it to the edge service as shown in this figure here. The fact that cloud and edge applications are usually in different are distributed, means they are usually in different locations and even have time differences. Impose a huge challenge on the data transfer, since the network instability can cause high latency, which is not tolerated in some cases. For example, the cloud service is in London, but the edge service in Newcastle. Moreover, we need to pay for computing, storage, or other additional functions when we use cloud services. However, researchers found that the Raspberry Pi is a device commonly used in the IoT fields. Its performance is offering up to 3 times the computing performance of commonly used service CPUs. When the powerful computing power of edge services is fully utilized, network transmission times and costs of IoT deployments will be significantly reduced. But we need a solution to simplify the deployment, management, and combination of edge and cloud applications, as well as the management and control of data flows. The solution is tie edge and cloud service resources together for use. So I propose a data flow orchestration to meet the requirements. The next section is related work. I read some papers and analysis and concluded their gaps and what features and orchestration needs. Here, there are 7 points I highlighted. These 7 points should be considered when designing and developing an orchestration. Cross-platform means that the orchestration should be able to be deployed in platforms with different environments, different operational system environments, such as Mac OS, Windows, and Linux. The second one is publish subscriber pattern. This is which is popular pattern in IoT field. A system designed following the publish-subscribe pattern can loosely couple publishers and subscribers and can support the broadcasting of messages through the implementation of the message queues. Thirdly, we need to consider the message accuracy and latency when we design the workflow of the orchestration, like what I said in the introduction. Ensuring low latency and accuracy of the message is important. The next is various data models. In IoT system, the formats of data used for transmission is various, such as JSON, binary, batch, and string. As data flow orchestration across the cloud and edge services, it should support the processing and transmitting of these kinds of data. The next one is visibility and accessibility of resources. Traditionally, cloud services and edge services are distributed. They transmit data over the internet and are influenced by different network environments, such as public network and private network. There is a firewall between the cloud service and edge service to protect the private network. So the firewalls also have an impact on the visibility and accessibility of services behind the firewalls. The orchestration platform should break the limits during managing the data flows. Then, through a discussion of service-oriented architecture in my dissertation, I acknowledge the deployment of microservices on edge services is feasible. The last one is the developer friendly. The orchestration platform is originally developed to reduce the workflow of developers and service deployers. So the orchestration needs to be able to dynamically manage the configuration files. If not, for example, an orchestration needs to manage the data flow and often needs to make changes to the configure files, such as routing table, and it restart the service to make the changes take effect. It is very annoying, I think. So, data flow orchestration needs to achieve these 7 points. Then, let me introduce the design of the orchestration. This figure shows the overview of the orchestration. You could see from this picture, the orchestration includes a centralized controller here, 2 NoSQL database here, and 3 key components here. Kubernetes is responsible for deploying applications on edge and cloud services, and Prometheus is responsible for monitoring these services. Then the orchestration can be divided into 2 parts, control flow and data flow. Control flow is responsible for deploying and managing edge and cloud applications and their resources. But in this project, the data flow is the star of the show. Well, this figure shows the overview of data flow architecture. The data flow controller includes 2 parts, a scheduler, a NoSQL database. We use Redis here. The scheduler plays a key role in the control of the data flow. Meanwhile, Redis here is used to store the routing table. When the scheduler receives a REST request from users, it makes a decision based on the content of the request. Then data sources here give some examples of the types of data being transferred, such as byte array, string, JSON. Moreover, RabbitMQ treats the remainder of data flow, such as service-to-service transmission. In addition, the data processor here will be made available for each microservices, with data processor. Services can convert data from a byte array to the format required by service, or from the services preferred form to a byte array. Next, I would like to introduce the workflow of data flow orchestration. Firstly, this figure shows the state transition of the data flow orchestration. In the beginning, the orchestration will load configure, initialize connections and exchanges, then load the YAML file. When after the orchestration has been started, the type of request will influence the system state and lead to different branches and to different endpoints. In the transmission branch, the orchestration checks whether the routing key is empty in the venue read from Redis, and decides whether it is a need to create a routing key. However, a notice queue name or a routing key for transmission will be returned to the new service or the sender. This figure shows the change in activity of the publisher and orchestration during sending of a message. When the orchestration receives a transmission request, it is necessary to validate the parameters within the request body. After that, the orchestration returns the routing key to the publisher, and publisher start to send a message. Now, particularly, this figure shows the progress of requesting and consuming data for a new service. When a new service requests and receives a new queue name from the data flow orchestration, the services should listen to the queue as a channel to get the details of transmission. I would like to say there are two exchanges for managing the data flow. The transmission exchange is responsible for forwarding messages between publishers and subscribers, while the noticing exchanges is responsible for notifying subscriber about which queue needs to be listened to. So subscriber knows the queue it needs to listen to, then it runs a new thread to consume the message for proposing, and it runs a new thread to consume the message for processing from transmission exchanges. Well, the last section is the demonstration. Redis and RabbitMQ and other middleware are running in my virtual machine. Then actually I simulated two clients, one sender and one receiver, means one publisher, one subscriber. Each client have their methods to send and process data to or from the RabbitMQ. The first thing of sender is to get the routing key here. Then package their message and send message to exchanges like here. Then I set up three types of tests. The first one is JSON test. The second is binary test. The third one is string test. Then, however, for the receiver here, it needs to register in the orchestration firstly and get the noticing queue name here, and it need to consume the queue. Then if there are messages consumed by subscriber, the subscriber will new a thread to deal with this the request of transmission here. For proposing string, the subscribers needs to connect to the string client and start consume here. But for other two type of messages, it just needs to consume the transmission queue here. Okay, let's start. Firstly, I need to start a subscriber. We could see there is a image in the sender test, but in receiver test there is no any image. Then we start sender. Then you could see the result. This is string message, and this is bunch or JSON message. Then the image is here. The new image is here, received from the sender. Okay, this is the test. Then I need to store it. In addition, the orchestration supports the RESTful API, so I just need to run the main thread to initial the RESTful API client. When the orchestration has been started, I could access the results via HTTP use my browser like this, like here. I enter the URL and I can get the JSON, get the result from the orchestration. This is the handler. And This is the router. I enter this URL, then I can get a get a response from the orchestration. Okay, this is all what I want to say. Thank you for listening and have a nice day.